Hi friends, in the last lecture of the investigation of the molecular structure, that is a lecture number 7, we have discussed the rotation spectra for the diatomic molecule. So here the molecule which possess the permanent dipole moment, only those molecule they are the microactive, that means they give the microwave spectra. So all of you know that the microwave spectra, it is called as the rotation spectra. So here when the molecule interact with the microwave radiation, that is a 10 raised to 5 nanometer to 10 raised to 7 nanometer, here the molecule give the rotation spectra or the microwave spectra. So here when we consider the microwave spectra for the diatomic molecule, the selection rule is delta J is equal to plus minus 1. There are two types of the spectra, that is a absorption spectra as well as the emission spectra. But here generally here the absorption spectra is considered and the selection rule is delta J is equal to plus minus 1. When we consider the rotation spectra or the microwave spectra for the diatomic molecule, so here delta J is equal to plus 1 or delta J is equal to minus 1. When we consider the transition from 0 to 1, here the in the rotation spectra, the first line is obtained at the twice b centimeter inverse. When we consider the second transition, that is a 1 to 2, then the second line in the spectrum, it is obtained at the 4b centimeter inverse. The next year from 2 to 3, the line is 6b centimeter inverse and so on. So 8b centimeter inverse, 10b centimeter inverse, 12b centimeter inverse and so on. So here when we consider the spacing between the two lines in the rotation spectra, the spacing is a twice b centimeter inverse. So here already we have discussed this in the rotation spectra or the microwave spectra for the diatomic molecule. So here in this lecture we are going to consider the application of the rotation spectra, then here the isotopes and the microwave spectroscopy as well as the merits and the demerits of the rotation spectra. So friends, let us consider one by one. So here number 1 is the applications of the rotation spectrum. So here the first application from the absorption spectrum of the molecules, the spacing between the two lines, it is a twice b, it can be calculated. So here just we have discussed, that is the spacing between the two lines in the rotation spectra, it is a twice b centimeter inverse. So here from the spacing, here we can calculate the b. So here just spacing divided by 2, here we get the value of the b. So here we know that b is the rotational constant and here b is equal to h upon 8 pi square IC. So here from this equation, just by substituting the value of the b. So how the value of the b is obtained? So here if we have the absorption spectrum of the diatomic molecule, the spacing between the two line is, that is a twice b. So from the spacing we can find out the b, just substitute the value of the b here. Then here h is the Planck constant, the value of the pi 3.14 and c is the velocity of the light. By substituting all these values we can find out the I is the moment of inertia. So here again we know that I is equal to mu into r0 square or I is equal to mu into r square. So here the value of the I is obtained from this expression, substitute the value of the I here. Then here mu is the reduced mass. So how the reduced mass is calculated? So with the help of this formula, that is a mu is equal to m1 into m2 divided by m1 plus m2. Here in this way the reduced mass for the diatomic molecule is calculated. Substitute the value of the I, moment of inertia, as well as the reduced mass. Here we can find out the bond length of the diatomic molecule. So just substituting the value of the m1, m2 and here I, here we can determine the bond length. So this is the first application of the rotation spectrum. Then here the second application, that is a atomic masses of the different isotope can also be found out from the rotation spectra. So here in the next point we are going to consider the detail, that is with the help of the rotation spectra, how the mass of the isotopes can be calculated. This is the second application. Then here third application, comparison of the absorption capacities can be used determination of the abundance of the isotopes. So friends, here since each molecule possesses a unique moment of inertia depending on the particular isotopic nuclei present. So from the relative intensity of the spectral line, when we consider the absorption spectrum, and here from the absorption spectrum of the diatomic molecule. So, here from the relative intensity of the spectral line, the abundance of the isotopes can be determined or can be obtained. This is the third application. Then here microwave technique is also useful in locating the position of isotopic substitution within the molecule. So, here these are the some important application of the rotation spectra or the microwave spectra. Then here limitation of the rotation spectra, that is a demerits of the rotation spectra. So, here all of you know that rotation spectra, it is useful only for the substances having the permanent dipole moment. That means, here the only the polar molecule they give the rotation spectra, that means they are the microwave active or the rotational active, while the non-polar molecule that does not have the dipole moment. So, here they are the microwave inactive, that means they does not give the rotation spectra. So, this is the first limitation. Then here rotation spectra or the microwave spectra, it is useful for the gases and easily volatile substances, because rotations is free in the gaseous state only. In the liquid or the solution state, the rotations are not free, but must restricted by intermolecular forces. So, that here this is the limitation. So, here this rotation spectra, it is useful or it is applicable only for the substances in the gaseous state or which can be easily converted into the volatile state. So, here this is the second limitation or this is the second drawback. Then here the microwave spectra or the rotation spectra, it is useful for the diatomic molecule having permanent dipole moment, that for the heteronuclear diatomic molecule such as HCl, carbon monoxide, then here HCN or hydrogen iodide, only these molecules they are the microwave active. While here when we consider the homonuclear diatomic molecule, so H2, O2, N2, Cl2, they do not have the permanent dipole moment, hence they cannot be studied with the help of the rotation spectra. Then here the last one is in a triatomic and as well as in the tetraatomic and polyatomic molecule, there are many moment of inertia. So, here in case of the tetraatomic as well as the polyatomic and the triatomic molecules, so there are many moment of inertia. Therefore, a single moment of inertia is not sufficient to give the complete detail of the molecular structure. So, here this triatomic, tetraatomic and polyatomic molecules they are not studied in case of the microwave spectra or in case of the rotation spectra. So, here these are the certain limitation or the shortcoming or the drawback of the rotation spectra. Then next point is the isotopes and microwave spectroscopy. So, here how the microwave spectroscopy is very useful to determine the mass of the isotope, that part we are going to consider in this point. So, here when a particular atom in a molecule is replaced by its isotopes, so there is no appreciable change in the internuclear distance. So, here let us consider the case of the carbon monoxide. So, here in case of the CO, here the carbon 12 is used. So, instead of carbon 12, if we use the carbon 13, so here there is no appreciable change in the internuclear distance, that means there is no change in the bond length. When we move from carbon 12 to carbon 13, so here there is no change in the wavelength, but here upon isotopic substitution there is a appreciable change in the total mass. So, here the total mass is changes, that is why here there is a change in the reduced mass. So, here when we consider the reduced mass of the carbon monoxide where the carbon 12 is used as well as the carbon monoxide where the carbon 13 is used. So, here there is a change in the reduced mass when we use the carbon 13. So, here when the reduced mass is changed, the moment of inertia is also changed. So, here I is equal to mu into r0 square. So, here the moment of inertia is also changed as well as the rotational constant, that is the value of the B, it is also changed while substituting the isotope of that particular atom. So, here this is the first change. So, here again the same example, that is a carbon monoxide, to carbon monoxide where carbon 13 is used instead of the carbon 12. So, there is an increase in the mass and here there is a decrease in the value of the B. That means, here the reduced mass is increases while the value of the rotational constant it is a decreases. So, here the rotational constant it is denoted by B for the carbon monoxide where the carbon 12 is used and here it is a greater than the rotational constant say B dash in carbon monoxide where carbon 13 is used. That means, here the value of the B is greater than the value of the B dash. this change will be reflected in the rotational energy level of the molecule, and for the above change there occurs lowering of the rotational energy level. So, friends, here when we consider this carbon monoxide where the carbon 12 is used, and here when this carbon 12 is replaced with the carbon 13, that is isotope of the carbon. So, here when we consider the energy levels for the carbon monoxide where the carbon 13 used, what is the observation? There is a lowering of rotational energy levels. Due to this reason, it is observed that heavier species such as the carbon 13 shows a smaller separation between the line, that is the twice B dash, than that of the line lighter one, that is a 2B in the microspectra. That means, here when we consider the microspectra for the carbon monoxide where the carbon 12 is used, as well as the carbon monoxide where the carbon 13 is used. So, what is the observation? The spacing between the line in the carbon monoxide where carbon 13 is used, that spacing is decreases as compared to the lighter one, that is the carbon monoxide where the carbon 12 is used. So, here this information it can be used to find out the isotope of the or the mass of the isotopes. So, let us consider that point. So, here the effect of isotopic substitution upon the microspectrum may be used or may be useful to calculate or to evaluate the atomic mass of the different isotope by comparing the spacing between the line. Again, here we are going to consider the example of the carbon monoxide. So, here again carbon monoxide where carbon 12 is used, here the spacing between the two line it is a 3.84235 centimeter inverse, while that of in the carbon monoxide where the carbon 13 is used, the spacing is 3.37 centimeter inverse. So, here the value of the B determined. So, here this is the twice B, this is also twice B. From this we can find out the B. So, here the B is equal to 1.92118 centimeter, and here the B dash it is 1.83669 centimeter. What is the B dash? B dash is the rotational constant for the carbon monoxide where the carbon 13 is used. So, here when we compare these two values, so here what we observe that here we observe that the value of the B dash is less than the value of the B. So, here after substituting the isotope of that atom, here there is a decrease in the value of the rotational constant. So, here where this prime refer to the heavier molecule. So, here beta dash or beta prime it can be referred to the heavier molecule. So, here B upon B dash is equal to. So, again we know that value of the B is H upon 8 pi square IC. So, here this is the value of the B divided by B dash, that is divided by H upon 8 pi square I dash C. So, here this can be written as into 8 pi square I dash C divided by H. So, here 8 pi square C, here also 8 pi square C, this 2 will be cancelled, and here so B upon B dash is equal to that is I dash upon I is equal to mu dash upon mu. So, here when we substitute the value of this B and B dash here, so here we have the formula mu dash divided by mu is equal to 1.046. So, with the help of this we can find out the atomic mass of the isotope just by substituting the value of the mu dash as well as the mu. So, here where mu is the reduced mass and the internuclear distance is considered unchanged by isotopic substitution. So, here again let us consider the example of this carbon monoxide. So, here taking the mass of the oxygen, it is a 15.9994 and here the mass of the carbon is 12. So, here in the carbon monoxide when the carbon 12 is used. So, let us consider this carbon monoxide where carbon 13 is used. Again here the mass of the oxygen it is a 15.9994 and here we have to find out this mass of the carbon 13 by using this formula, that is a mu dash divided by mu is equal to 1.046. This mu is the reduced mass for the carbon monoxide where the carbon 12 is used, while this mu dash again it is the reduced mass for the carbon monoxide where carbon 13 is used. So, substituting the value of the mu dash divided by mu is equal to 1.04. So, here 15.9994 m dash divided by 15.9994 m into 12 plus 15.994 divided by 12 into 15.994. So, here when we solve this with the help of this equation, here we can find out the value of this m dash, and here when we solve this, the value of the m dash, that is the atomic weight or atomic mass of the carbon 13, it is found to be 13.007. So, with the help of the rotation spectra or the microspectra, we can find out the atomic mass of the isotope. So, this is the important application of the rotation spectra. So, let us consider the diagram, the effect of isotopic substitution. So, here again carbon monoxide where the carbon 12 is used, here the carbon monoxide where the carbon 13 is used. So, mu is less than mu dash, while here B is greater than B dash. So, here this is the spacing between the two lines. So, here this is the regular carbon monoxide where carbon 12 is used. So, these are the rotational energy level. So, here these are the transition. This is the first transition 0 to 1, this is the 1 to 2, 2 to 3, 3 to 4, 4 to 5 and 5 to 6. So, here these lines are observed at twice B, 4B, 6B, 8B, 10B, 12B and so on. When the carbon 12 is replaced with the carbon 13, there is a decrease in the rotational energy. So, here this is the decrease in the rotational energy when the carbon 13 is used, while this is a transition 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5. Again here when the transition takes place as per selection rule, delta J is equal to +1. So, here the spacing between the line is decreases. Here the spacing between the line is decreases, that means the value of the B dash is less than the value of the B. So, here this is the effect of isotopic substitution on the rotation spectra. But here with the help of this we can determine the mass of the isotope for the diatomic molecule. So, here this is the important application of the rotation spectra or the microwave spectra. So, friends, in today's lecture we have discussed the application of the rotation spectra as well as the demerits or the disadvantages or the limitation of the microwave or the rotation spectra, and here with the help of the rotation spectra how the mass of the isotope can be calculated. So, friends, thank you.